Right, so this is lecture number 17. The last lecture we discussed about mass flow problems. So what is the rate of change of the momentum of a system for which mass is flowing in and out, right? We focused on a particular kind of problems, that was when the system was not accelerating. All the problems we considered, the system was moving with a constant velocity or it was stationary. So today we will discuss the second class of problems where the system is accelerating. So let's say we have a rocket. We'll start with that. The rocket has a mass of capital M. Now the mass of the rocket will change with time. The rocket has a fuel in it that is burning. So at time t, this is how I define my system. That's the mass of the rocket. Plus, just for definition, I will say that there is a delta M. There is a delta M mass of fuel plus oxidizer that is about to burn. So when I say fuel, that means both fuel and oxidizer. It's about to burn. Okay. So at time t, my mass of the system is capital M plus delta small m. That's how I've defined my system. T plus delta t, this delta M mass of fuel has burned and been released from the rocket, but still my system has to have that same amount of mass because that's how we define systems. So the envelope of system looks like this at t plus delta t. If you wanted, you could have taken capital M as the mass of the system, and then at time t plus delta t, the rocket is M minus delta M and delta M has left. It's up to you how you define it. We have used this definition. Now the rocket was moving at a velocity of v at time t, and at time t plus delta t, the rockets now accelerated. That's the whole idea of burning a fuel in a rocket, and the fuel is leaving the rocket at a relative speed of u. The gas leaves the rocket at a relative speed or relative velocity of u. So the delta M mass, that's the gases, at time t plus delta t have a velocity which is u plus v plus delta v. So we are considering all this from a Newtonian frame, that is outside the rocket, because if you sit on the rocket, then the rocket is accelerating. Newton's laws will not be applicable. So we are analyzing this from, let's say, ground frame or from a fixed frame in space. Now this gas velocity that is ejected from the rocket, that is not a function of it's not a function of v. The gases are released relative to rocket depending on what is the design of your nozzle, what is the fuel, what is the propellant you are using, and these conditions. It's not a function of how fast the rocket is moving. So u will be independent of v. Is that clear? Good. So now that we have defined the system, now we can apply the Newton's second law as we define as we apply this for systems. So the linear momentum at time t is capital M times v plus delta small m times v, because both were moving with a velocity of v at time t. At time t plus delta t, the rocket now moves at v plus delta v, and the gases because of the relative velocity they have with respect to the rocket from the absolute frame or the fixed frame, the gases have a velocity of v plus delta v plus u. So the momentum is delta small m times this quantity. For those who have joined late, we are doing we're discussing the rocket flow problem. So we have to remember that a system has to be defined. You can only apply Newton's second law, whatever form you are using, for a collection of mass particles, because Newton's second law says that the force acting on a system of particles is the time rate change of the momentum of that system of particles. You have to remember what mass particles you have taken. And it was, we obtained this from the law that force acting on one particle is equal to mass times acceleration of that one particle. If you remember how we get these things, then the confusion will not occur. Let's find dp by dt. In this sum of three quantities that we have, now delta v or whatever delta of something is small as compared to the quantities. So if you take m times delta v and you add delta m times delta v, then delta m and delta v are both small. So small times small becomes super small. You know that, right? 0.01 times 0.01 is 0.0001, and if you add that to 0.01, that's almost 0.01. So in this sum of three quantities, this quantity can be neglected. Remember, it's not zero. We are just neglecting it because we are adding this quantity to two other quantities which are much larger in magnitude. So the contribution of this quantity to the overall sum is negligible. So this is the time rate change of linear momentum. Is that clear? Now the quantity d small m by dt and d capital M by dt, they are related. Somebody tell me how they are related. Small m is the mass of the gases being released and capital M is the mass of the rocket. Right? So this is the mass of the rocket, that's constant, plus fuel. So from that, if you differentiate small m plus capital M being equal to constant, you get this. The rate at which the rocket's mass is decreasing with time is the rate at which, if you were able to collect all the gases being released, that mass is being increased with time. So this allows me to write dp by dt in terms of only one of the masses. So we'll use the mass of the rocket. So this is the time rate change of the momentum of the system. This is equal to the external force acting on the system. Let's apply it to a problem to understand this better, to develop some intuition for this expression that we have derived. So let's say you have a rocket in space. So what that means is the external force acting on the rocket is 0. There is no gravitational pull. It's left the gravitational pull of all planets. It's in free space. So the external force acting on the rocket is 0. You have to find the expression for the velocity of the rocket. As a function of the mass of the rocket. Because the mass of the rocket will change. It will burn fuel, its mass will decrease with time. So we want to find out how this velocity of the rocket, because the rocket is accelerating as the fuel burns, the rocket accelerates. So I want to find out how this velocity is depending on the mass of the rocket, given that you start with a certain velocity and certain mass. So let's say initially it's given to us that the rocket starts with a velocity of 0. So it starts with a 0 velocity at a time initial equal to 0. And the mass of the rocket at that time was m0. I have a mass of the rocket, rocket plus fuel, that I am launching. Well, not launching because then we have gravitational pull. Let's say in space it was freely moving, and then you want to accelerate it for some reason to reach some other planet. Then you burn fuel, and when you burn fuel, before that the mass was m0. From some frame its velocity was 0, and you call that time t initial, that is equal to 0. I want to find out how now, once I start burning the fuel, the velocity of the rocket changes with changing mass. Is the problem clear? Now we can also assume that u is equal to a constant velocity. So you remember, u was the relative velocity of the gases that leave the rocket. That is a function, that is not a function of v, it's only a function of how you are burning the propellant. That's how you decide from inside what is the rate of propellant you want to burn. So let's say we are keeping it to be constant throughout we are ensuring that the propellant is burned in such a way so that u stays constant. That is a reasonable assumption, but that is a given in the problem. U can change as well, but u changes depending on how you control the burning. So let's assume u is constant and then apply this variable mass flow problem expression. So, the external force that's given to be 0 in the problem. So, what that gives us so if we integrate this from an initial mass of m naught to m, and when the mass was m naught, the velocity was 0 to some general variable velocity v. I know that m naught is larger than m final. Right, because the fuel is burning. So, I would rather keep it m naught in the numerator, because m naught by mf is greater than 1. So, this is the expression for the final velocity as a function of u, m naught and m. So, I can now remove f. So, that is the velocity at any time given the mass at that time. Now, of course, I mean small u, the masses leave in a direction which is opposite to the movement of the rocket. So, that negative sign makes sense. The rocket moves in the opposite direction of u. There is also something, another thing interesting. There is no effect of time. So, it does not matter if you burn the gases slowly or quickly, assuming that u is still constant, but dynamically there is no effect of time. You can take all the time you want and burn the gases slowly, as long as you can maintain that u. So, u can be maintained by nozzle effects as well. It does not really depend on only the gas flow rate or the burn rate. It can also depend on how you design the nozzle. So, for it does not really matter how fast or at what rate you burn the gases. That is non-intuitive, because when a rocket launches, you burn the gases really, really fast. That is what makes it very interesting to watch. But in space, it does not really matter. So, the final velocity that you want to achieve is only a function of the amount of mass you have burnt. That is it. If for some reason I am designing this for space, and if I burn the gases very quickly, the temperature increases, because I cannot get rid of that amount of heat that quickly. So, for that my temperature will increase in the engine, and that could lead to a meltdown, and because the materials I am dealing with do not allow high temperatures. So, this is fine for me, because I can burn the gases slowly and still achieve the same velocity, no problem. Okay. So, before we look at the next problem, where now we are launching the rocket from the surface of Earth, I would want you to look at this expression, because most of you will get confused at some stage after a few lectures or towards the end sem. When you look at this expression, you will say that the mass times acceleration, m times dv by dt, is equal to the net force. That is what the net force is, right? Force acting on a body is its mass times its acceleration, that time rate change of its velocity. but the external force here is 0. And of course, I'm just trying to confuse you. We have derived very elegantly that the net force acting, the external force acting on the system is not only its mass times acceleration, there is also an effect because of the changing mass. That's the whole idea of having this discussion. But at some stage, most of us get confused, and we will read books as you go further into engineering. You will actually read rocket, work with those applications. You will say that we are modeling the rocket. There is a force, a thrust force because of the burning gases, that is T, and this T is equal to the mass times the acceleration of the rocket. And this T is given as dm by dt times u. And if you apply that, you actually end up getting the same thing, this one. But typically, I mean, see, there is a lot of interesting dynamics happening in the rocket, and we have been able to capture that to some extent by ensuring, by taking the effect of burning gases. So once we have figured this out, you can model this system as an external thrust acting on the system. Actually, there is no, I mean, it's not an external force. It's internal force because of the interaction of the molecules of gases with the engine, or the walls of the engine, because so there's a sudden explosion of gases. They have high pressure. They apply pressure on all walls except that one ending is open. So the net effect the gases have on the rocket is to give it a push up. And if you look at the gases, the forces acting on them, then the force on them is downwards because of the one wall of the rocket. If you had closed all the walls of the engine, nothing would happen. But if you allow the gas to leave, then because of the pressure differential, there is a net force. Okay, so if you see this, this is the model. The actual expression is what we have learned. So don't get confused. But this is done. We do this, we say that the thrust acting on the rocket is equal to, is there because there is a gas burning. So it is equal to dm by dt times the speed with which the gases leave, or the velocity with which the gases leave. In this case, it's vector we are talking about. But of course, you don't have to get confused with this, because I will suggest you use this expression. Right. So next problem. This time we have an external force, that is the force due to the Earth's gravity. So the rocket is, let's say, about to launch. So there is a gravity force. The direction of gravity this way is, rocket wants to launch. Would be minus g. Right? No, it's a vector. I have not told you, we'll put the vector sign. So from here to here, it's all right, right? Later we will substitute g vector is equal to g magnitude times minus j hat. Let's say this is that direction. This starts from 0 velocity. Let's say start from 0 time. We will substitute the vectors now. So Vf, we will call it V magnitude times j hat, because we have an intuition that it flies up. If for some reason it was flying down, then I will get a negative sign for Vf magnitude. Similarly, g is acting downwards, so we will take g vector as minus g magnitude times j hat. If you want to solve a problem where g is actually acting upwards, then you simply have to change the magnitude of that in the final expression. But I will suggest you work with the vector expressions, or if you have, there is not much of a derivation here, you start with, always try to start with this expression. Let us substitute these vectors. The final velocity expression for a rocket that is launching from the surface of Earth, or from any planet for that matter, is given as this. So we see that now we have an extra term because of the Earth's gravitational pull, that is minus g times t. Let's get rid of the f here. So now we understand why we burn gases in a rocket when it's about to launch at such a high rate. You have to compensate for that minus gt. If you burn the gases really slowly, nothing will happen. You have an intuition for that. Very slowly you burn a small amount of, you burn a candle, nothing will happen. Okay. Do you have any questions? Let's give you a problem now, and I will ask you to work on it. So this becomes some sort of a tutorial for this section on mass flow problems. This is the problem. An air-breathing jet aircraft of total mass m flying with a constant speed v. So this is the earlier case, constant speed, no acceleration here, consumes air at a mass rate of ma prime. So this is an air-breathing jet. You have these jets. They, they don't have oxidizers as such. So to burn the fuel at a large flow, at a high rate, you need lots of oxygen. So what it does is, it has an opening in the front or at the bottom where it breathes air, because it's moving very fast, so it can also breathe air very fast. So it breathes air at a mass flow rate of ma prime and exhausts burnt gases. So this air, when it combines with a small amount of fuel that burns, so the exhaust gases are released at the rate of mg prime with a relative speed of u with respect to the jet aircraft. Fuel is consumed at a constant rate of mf prime. Now, mf prime is very small as compared to ma prime. The total aerodynamic forces acting on the aircraft are the lift L. So when an aircraft flies in air, it experiences a drag force and a lift force. The net force is split into two parts. One is a drag force, which is in the direction of flight, opposite to the direction of flight, and a lift force which is perpendicular to that. Okay? So you have two components of forces, L and D, that are given to you, because we don't know aerodynamics here. So let's, if you learn aerodynamics, mechanical engineers will learn what the expression for this is as a function of the speed of the jet. But for now, let us say that is given to us. So we have to write the equation of motion. So you have to write the external force is equal to dp by dt, where this dp by dt has to be written in terms of the mass flow rates here and the velocities v and u. Can I please ask you to try it yourself for a couple of minutes? I'll walk around and you can ask questions. We can work in any frame we want. So I'm applying this relative to the jet frame. It's also moving with a constant speed v. So and the other thing we do is we consider the fuel and air separately. So let's see air first, because the change in momentum for the fuel plus air together will result in the overall force acting on the. I mean, if you wanted to derive from first principles, you could do that. You'll get the same. So we'll consider them separately and take the rate of change of momentum because of fuel and air separately, and that will become the total force acting on the system. If I take air starting with the x direction, because we're talking about vectors here, x direction is the direction along the direction of motion, and y is the direction that is normal to the direction of motion. M prime is ma prime because we are talking about air here. So air enters and air leaves. Although whatever is leaving, the gases, has a mix of air and a burnt fuel. But I am only taking the air part right now. The burnt fuel I will take in fuel, because I know this mass balance. M prime A is equal to M prime gas plus M prime fuel. Sorry, the other way around. Some mass of air enters at a given in a unit time. In that time, fuel burns and gets added, and the exhaust leaves. I am ensuring that there is no gas getting collected inside. That makes sense. We don't want to collect exhaust gases inside the engine, inside the jet. Okay. So the exhaust gases has a contribution from air and a contribution from fuel. So we will take the contribution from air first. So the air enters and leaves. The air enters, the air is stationary, the jet is moving. So relative to jet, the air is entering at a speed of minus v, and it is leaving at a speed of minus u, because that's given to us. Related to the jet, the air leaves at u. Okay. So we apply this. This is not a vector. This is the magnitude in x direction. This is one contribution towards the force. So we will call this F x air. There is no y contribution because of this, because I have taken my x axis in such a way so that the V out and V in actually were these magnitudes. So let us take fuel now. You want to substitute these values yourself. So what is V out x? Minus u. Fuels leaving with the exhaust. And what is V next? 0. Fuel initially was moving with the jet. So from the jet's frame, the fuel's stationary. Then what is the net external net force acting in the x direction? Is that right? Now looking at the free body diagram, what is the force acting in the x direction? Drag has a contribution and a component of mg also has a contribution. This g is a subscript. This is the equation of motion for this problem. Theta here is this angle. Now this right hand side, typically what happens is mf prime divided by ma prime is close to 0, or it's a very small quantity. You can simply write ma prime the amount of air that's entering is much larger than the amount of fuel you burn. So we can actually write mg prime approximately equal to ma prime. Now, if you were to model this as a jet flying with a thrust, what will be the thrust here? It was on the right hand side, because in the x direction it's the thrust that will balance whatever's acting against it. There's a contribution from mg that acts against it, tries to slow down the aeroplane, and there's a drag, the aerodynamics drag of air that is trying to slow it down, but you want to move the aeroplane at the same speed v, so you have to burn gases. So we model it as a thrust, and that thrust is nothing but what's on the right hand side. So this is our modeled thrust. So we can check if mg prime is 0, we get no thrust. Mg prime is the rate at which the gases are exhausting or entering, it's almost the same. If u is equal to v, you don't get any thrust. Okay. If u is 0, reverse. You get a negative thrust. So we will stop here now. I hope you understand how to solve problems on variable mass flow. We'll see you on Monday.